Hello again, students, and welcome to a new nugget on biomass for energy. The previous nugget dealt with the first operations, harvesting and collecting the biomass at an accessible roadside location. I mentioned that I count the first steps in the supply system to be finished once the biomass is on board the first vehicle. And what we will talk about today is the loading and the transport. Transports can be done by different means, but I will concentrate on trucks since they are the most important. However, the way to compute transport cost is the same whether for trains or planes or boats. So you will learn a general, mode of attack. Looking at this slide, you will notice that following the harvesting and collection operations, there are transports and there are storages. And then, finally, the biomass is used. The use can be different. It can be an energy extraction process to generate heat, cooling and electricity. Or it can be a conversion process to make something new, but in that case not to extract the energy, like a pyrolysis process or gasification or something else. Anyway, we already dealt with the first steps in the previous nugget, and lessons 2 and 3 have taught you about conversion and energy extraction processes. And the next nugget will treat storage and the risks and problems associated with the storing of biomass. So what we shall do now is to have a little look at the transport and how the material should be treated to facilitate and enhance the transports. I will use wood fuel as an example for all reasoning in this nugget, and I do that because, as you remember from the Busy Plan Handbook chapters on resources, is forest residues one of the major resources as seen from a global point of view. This may certainly look different in your region, but what I will try to do is to talk about general considerations equally applicable to all types of biomass, but then just use forest fuels for an illustration. Let us first state that any biomass-based energy supply system is first and foremost a local or a regional affair. The infrastructure shall be kept local so as to promote local jobs. Another reason to keep it local is to minimize energy losses through excessive transports. And then there is the circular economy thing. Ash shall be recirculated to the harvesting site so as to economize with nutrients. Remember that the word economy as such has nothing to do with coins and banknotes. Now, there is certainly an international and overseas trade of wood fuels. Wood pellets are imported to Europe from Canada, just to mention one. But that type of long-distance transport is out of scope for this nugget. In some cases may railway transport be an option, but in most cases not. Railway transport is superior if there is a huge resource at one end of the country, so that massive amounts of material must be extracted from a limited area and transported a long distance. In that case, and with the railway loading terminal placed centrally, will the advantage of rail transports be fully utilized. But there will be at the very least one loading and unloading operation, namely when the trucks from the felling sites are unloaded at the rail terminal and the railway cars are loaded. Each and every loading and unloading operation, unless the material is handled in closed containers, will produce material losses. Solid biomass will always release dust when poured from one vessel to another. And if each loading and unloading operation generates a material loss of 1%, you will want to keep a low number of such operations in the system. Unless each and every end user in this case has a railway track on site, there will again be one loading and unloading operation at the receiving end. But anyway, if the raw biomass is available at a limited area far away from where the end users are located, then is railway transport to be recommended. But in the vast majority of cases is road transport by trucks the preferred way to solve the transport problems. This video shows a small mobile chipper working at a roadside windrow in Sweden. Look at the video twice, and the second time pay special attention to the small container attached to the chipper. This is to save weight and thus save the soil from damage, but the price paid is more driving. Into the chipper is also fed the waxed paper that acted as a rain protection. The chipper mini container is emptied into larger containers transported 3 by 3 on a lorry and trailer. This is one common way for chips transports in Sweden. This sequence shows a chipping site in northwest Canada. You will notice that everything is a bit bigger, but otherwise it's about the same handling. In the video on the previous slide, you saw 2 examples of trucks. The system with small containers is favorable in case the tonnages are not too big. The problem is that the unloading of the containers is a complicated operation, since the container must be lifted, turned upside down, and then again put back in place. The truck you saw in the sequence from Canada had a huge volume and is apt for long transport distances. In that case was the loading area rear tipping, so the truck will be backed up to the unloading place and then just tip out the chips. But there are other types of trucks too. Common to all trucks aimed for road transport are that the external height of the truck is limited and that the external width is also limited. The height and width valid for your country will be available from your National Department of Transport or from some other national or federal authority. Just to give you an idea of how this can look, the uppermost link in this slide is to the Road Safety Authority of Ireland. And on that page you will find PDF documents to be downloaded giving you the detail of measures and weights allowed on Irish roads. With height and width limited, there is only one parameter left to set the volume capacity of the truck, and that is the length. Again, there will be limits set on a national or federal basis. But there is a trend towards longer and heavier trucks. An illustration of that can be found as one of the presentations made at the Federal European Workshop on gigaliners in 2009. The link to this workshop is the second one from the top in the slide. Log into that page, and a bit down on that page you will find a set of workshop presentations. Now download the one from the ACEA. That presentation is only a PDF version of a PowerPoint presentation, but it will give you an idea of combinations of trucks and trailers, and it will give you an idea of sizes and lengths. You should also download the report presenting an overview of technical aspects on longer and heavier vehicles. It must be remembered that the aim of that workshop was to promote trucks for road transport. So the workshop aimed at proving that longer and heavier trucks would be a positive development. But some of the facts presented in the 2 documents are useful for the purpose of this nugget, and we will come back to that. You may also want to look at the home page of the Federal European Ministry of Transport, DG Move. You will find in the menu the header Transport Modes. Opening that, you will find for road, rail and waterways link pages that may prove useful to you. But let us now go back to the wood chips transport for a moment. I said before that the 3-container type of transport is quite common in Sweden. Now let me modify that a little bit. Due to the complexity in the unloading operation, is this mainly used when transports end at a chips terminal. A terminal is an intermediate storage place, not an energy plant. When the transport ends at an energy plant, is another type of truck more common. The first video link shows a wood chips delivery to a paper mill, but the type of truck used is commonly used also for deliveries to energy plants. You will notice the side tipping function of the truck and the trailer. You will also notice the tarpaulin cover that hinders chips from blowing off the truck and hit other cars during the drive. And it also hinders road dust to enter the payload compartment and increase the ash content. This type of truck is available from several manufacturers. The second video shows another type of construction, in that case only for the trailer. In that case is the load emptied at the rear end of the trailer. It is obvious that if the truck had the same type of emptying system, then the trailer would first have to be disconnected before the truck could be emptied, so that would take some extra time. There are lots of different constructions and technical solutions, and we shall not dwell on that any longer now. Most logistic and transport companies will have presentations of their truck fleet available for customer inspection at their home pages. At random, I have selected a Russian transport company, FESS, and you will find the link to their English-speaking homepage in this slide. Open that page, go on to open the Useful menu, and then scroll down to find the heading Dimensions and Sizes of Trucks, and open that page. We will now do a simple estimate of the energy need for transportation. We assume wood chips with a dry density 400 kilos per cubic meter. We also assume a heating value for the dry substance at 19.5 megajoules per kilo. And then we assume 35% moisture content. Using these values, we can now estimate the density for the wet material, and we can compute the heating value. Loading a particulate material like chips will never fill the volume. There will always be holes between the individual particles. The porosity will depend on a lot of factors like particle size distribution, vibration, etc., but 40% porosity may be a realistic assumption. Using the porosity value and the solid density, we can now compute the bulk density. The solid material now fills only 60% of the total volume, so the bulk density is the average ratio of the mass of the material and the container volume. So then we find that a container 1 by 1 by 1 meter can take 366 kilos of our wet chips. And then we find a mean energy density for the load at 4,326 megajoules per meter cubed. Now we have to pick a vehicle, and in this case we will pick a truck. We might as well pick a boat or a barge or a railway car or an airplane, but we will now pick a car, we will pick a truck, and for simplicity I select the uppermost one in the FESS truck fleet presentation, the Eurotruck 82. This truck can load 82 cubic meters or 22 tons, and with the cargo we have, wet wood chips with a bulk density about 366 kilos per cubic meter, we will hit the weight limit. We are not allowed to load 30 tons, but we are allowed to load 60 cubic meters. So then a full truckload will be 72.2 megawatt hours. A truck company will never tell you how much diesel oil their trucks consume. And that is also for a good reason, because they don't know. The difference in fuel consumption between individual drivers can well be as big as plus minus 10%. So a total difference between two drivers at 20% is by no means impossible. So the only thing you can trust when it comes to diesel oil consumption and such is average values. Now open the PDF document about technical aspects of longer and heavier vehicles that you downloaded previously. Look at figure 7. I've copied it in this slide. To have a worst case scenario, I prefer to read from the upper curve. That is for 60-ton trucks with full trailers. And the smaller the truck, the higher is the fuel consumption. So I want to arrive at a high but not unrealistic value. The red arrows indicate that the total fuel consumption would be something just above, say 22 milliliters per ton kilometer. And then 22 ton kilometers per kilometer, since the load was 22 tons. So 220 ton kilometers per 10 kilometer driving. 4.84 liters of diesel oil per 10 kilometers. Make that 5 liters. Diesel density 0.85 kilos per liter yields 4.25 kilos of diesel oil. And then we have 10.5 kilowatt hours of energy per kilo of diesel oil. So even with this fairly small truck, not fully utilized, can the wet wood chips be transported more than 100 kilometers and the transport energy will still not reach 1% of the fuel energy. Generally speaking, will the total energy loss for a supply chain of an energy carrier be something about 5 to 15% of the total energy transported. In the previous nugget, we found that the initial steps, harvesting and collection of the raw biomass, might consume energy equal to about 5%, at the very most 10% of the energy contained in the biomass. Now we've found that the transport may consume another 1 to 2%. And the homework you are about to do will show an example of wood chipping. So the basic idea of this nugget is to demonstrate how to do rough estimates of the energy balance posts for the supply system. And that, in turn, is so that you shall be able to meet the arguments raised by those who claim that biomass for energy is uneconomic. But make no mistake, even though we have now seen that the supply can be made efficient, it is also possible to make very stupid systems and to make use of such biomass that will not be economic. So as a planner, you will always have to take good care and do a thorough analysis of the system so as to make it economic.